Okay, this is the third take of my video on this, and seriously, I'm going to pitch this iPad through a window if I make another mistake. Right, how does this work? This is a video about parallel line, no, it's not, it's about parallelograms, and it's about the diagonals in the parallelograms. They bisect each other. I'm going to prove to you why. Okay? Now, I'm not sure what the question was actually asked, because this has all been prompted by someone sending me an email saying, okay, can you tell me about diagonals in the parallelograms? Like, okay, fine, that's a random thing to ask, but whatevs. And she gave me a question link. I could not find the question for the life of me, so I'm just going to go with, okay, I want to prove this. If I'm wrong, just send me a picture of the question. I'm happily make you another video. This proof is a little bit involved. I've explained it twice before, which videos you will never ever see, and I've messed it up twice, as in, like, I've said something that would confuse you. It wasn't wrong, the maths is right. So just bear with me, I'll go slowly and we'll get this done. Here is a parallelogram. Definition of a parallelogram is you've got two equal sides, two pairs of equal sides rather, that are parallel to each other. So here I've decided to call my parallelogram ABCD, AD and BC are parallel, AB and CD are parallel. Their diagonals are the opposite corners, basically connected. And I said that both of these diagonals meet at a point M. I know it's a bit presumptuous to call M a midpoint, which I know is going to be a midpoint in a minute, but I'll prove it's a midpoint, and I'm just using the letter, so whatevs. How is this proof done? This proof is all about congruent triangles. I'm going to use congruent triangles and the sine rule, and that's all I need. Let's do some logic. Imagine, just look at G in the second diagram. These are the same parallelogram, by the way. Look at that angle G. I don't know what it is. Let's call it G. By Z angles, there'll be an equal G right at the bottom there. Because BC and AD are parallel, aren't they? And that diagonal is the same. Same thing with using BC and AD with H. Yeah? That H in the top right-hand corner will be mirrored by a H in the bottom left-hand corner. All well and good. Much the same argument for I and J. If I call the one slightly below G, J, and then use the parallel lines AB and CD rather, there'll be a J there, etc, etc, etc. Also, where two lines meet, I'm sure you know this from GCSE, you've got the angle at the top and the angle bottom are the same. I think they're called vertical angles, K and K, and L and L. I've just given them letters, names. I don't really need to know the numbers, and I'm not going to use them in any way, shape or form. Why am I doing this? Because I've got congruent triangles now. When you've got sides, you've got a side and two angles the same, you know you've got congruent triangles, and it's all well and good. We comfy? That's pretty much all I'm relying on here. By sine rule, I'm going to claim to you that AM equals CM. Yeah, and I've put cos. I don't mean cos as cos, I mean because I'm lazy. Because ABM and BMC are congruent. So let me explain that statement. Think about AM, the length AM, and I'm going to use the triangle ADM to make my point here. If you look at ADM, AM over, so we've got AM over sine G is the same as F over sine K, sine rule. If we do the same thing with BMC, we'll get MC, or CM, over sine G is the same as F over sine K. Now, you might have noticed that both of those statements are exactly the same. So that means both times you're going to get exactly the same answer. So AM is the same as CM, or AM is the same as MC, however you want to say that. So we've just proved that whatever the hell M is, it's going to be the bisector of that diagonal AC, because AM and MC are the same length. Okay? We're going to use this argument again. We're going to use this argument on BD. We are going to say that if you imagine the line, the length BM, that would be, BM would be, BM over sine I is the same as equals E over sine L. And if I did DM, DM would be DM over sine I equals E over sine L. Now, clever child will remember that that's just the same thing over again, so they're equal to each other. So therefore, BM equals MD. So therefore, M must be the midpoint of BD. So I've proved also that M bisects BD.